as they mentioned, we'll be talking about paint shop sustainability and basically kind of focusing on high transfer efficiency. So we'll cover some of the developments that we did within FANUC America, and then Marcel will transition into how these were adapted into their future paint shops, as well as a couple test cases. Yep,
Clicker?
He wanted to continue, I guess. Sorry about that. So we'll go through our high transfer efficiency testing and developments that we did within FANUC, and then transition into how GM accommodated that at their facilities. Strike two. Thank you. So overall agenda, I'll start out by talking through some of the sustainability areas that have been kind of mentioned here previously, address the ones that FANUC America could look at, and basically that's in the atomization with our application development and testing. Cover some of the testing, the trial results that we did both on flat panel and body TE testing, and then that morphed into a joint proof of concept validation process that GM and FANUC undertook within our lab. I'll transition then to Marcel. He'll go through some of the high transfer efficiency enablers that GM has seen, just beyond the paint savings, and kind of how that transitions into paint shop flexibility and some cost reduction drivers that they've seen. And then he'll wrap it up with a summary of how GM is taking that into production in their facilities. So when you look at paint shop sustainability and kind of what we've heard this morning on some of the E-coat and some of the other areas, you look at starting at the paint kitchen, going through the PTED systems, there's a lot of water, electricity, energy, air being used within the paint shop. On the robotic side, we do have color change, so there is paint waste and some solvent waste, but the majority of the time we're applying paint, and that's where high transfer efficiency can help with sustainability, as well as have some of the drivers into the overall paint shop. When you look at the booth air, you have temperature conditioned air, humidity conditioning, and just the volume of air that goes through the paint shop. So anything we can do to minimize the amount of paint being atomized and lost is a driver for enhancements. And then all the way through the full process. I know Marcel will touch on how high TE has helped them to be able to consider going to dry booths and the impact that they'll have on the sludge systems. But when you look at the overall sustainability when it comes to our application at FANUC America, it's really on the atomization. Those are the areas that we can address, that's what we can touch, and that's where we see the widest range of changes. I mentioned paint and solvent usage, but the overspray that collects within inside of the booth, that drives robot covers, it drives additional cleaning, applicator maintenance, all of those can be reduced by atomizing less material. And kind of one of the interesting pieces in talking with customers and seeing some of the marketing that's out in the industry is, what is high TE? We started looking at it as how can we get the closest to 100%? But that drives a lot of factors that I'll go into. If you think of an air atomized gun without electrostatics, very poor TE, but you add E-stats to that, in theory, it's a high TE applicator. So kind of got to understand what the customer needs, what they want, and how that impacts the process. So when we started our testing, basically, as I mentioned, we were trying to maximize TE. So that was minimizing the amount of paint that's being atomized, how much air is being used. So if you think of higher tip speeds, higher flow rates, higher throughput, that drives flow rates up, and higher volumes of paint being atomized requires more air for the turbine to spin to atomize it. More atomization requires more shaping air and then to pull that pattern back through. So we looked at focusing on trying to reduce all of those areas and basically try to optimize what that pattern size is. What we wanted to do at the end was basically have a pattern that's over the sheet metal, so you have charged paint going to the grounded vehicle, not having paint, a large pattern that as you get to the edge, all that paint falls off and is immediately lost. By reducing the amount of paint that is being atomized, it also increases our charge to particle ratio so that when that particle comes out, it'll immediately go to the panel and result in the high TE. And kind of where we started was with this flat panel testing, and that's the next section I'll go through. So where we started is kind of just a mathematical test. So here you make one pass across the standardized piece of foil, you apply the paint using the formula, you do a calculation, that gets your TE. In a lab setting, and Marcel attests to this, it gives you the best numbers. You know, had some that approached 100. I think we even had one at 104 in some of our testing, but that's where the math comes into it. But one of the drawbacks to this is it is a flat panel, and you know, since the Henry Ford days, I don't think I've seen a car that's a perfectly flat surface anymore. It makes this kind of a poor comparison to what will be seen in production. So this is kind of an example of this test. So what you see here is the robot goes out to the part, begins the atomization. We sit in a spot for a couple seconds, and that allows the entire process to become steady state. So the flow rate, bell speed, shaping air, electrostatics, that condition then is set, and then we make the transition across the panel. The amount of paint then that's gathered on that piece of foil is baked, and then that is what we use to measure the amount of solids that are on it, and we can do a ratio of what was applied against what's on the foil, and that results in our TE. This kind of shows the result of one of the tests that we had did. Here, looking at a few different variables. So we've got bell speeds going from low to high, tip speeds from 350 up to 650, and then varying the target distances. Here we did adjust flow rates to try to maintain the same amount of paint being applied to the part, just to try to keep some consistency in the data. Constants we held were basically holding 90 kV. We used our 45 millimeter bell cup, which results in a smaller 12-inch pattern. Again, the thought being trying to keep the pattern as small, optimized to the surface we're painting to maximize our transfer efficiency. And as you look at the chart, you kind of get what I think everybody has seen over history. You know, as you go faster, as you increase atomization energy, your transfer efficiency does drop. So what we've talked with a lot of customers is, you know, everybody has a high TE applicator. We can, with this data now, go and say, you know, what TE do you need in your paint shop to make all of your sustainability goals in effect? And then by using this data, we can kind of gauge number of robots, number of applicators, and how to optimize it for that customer. So based on this testing is when we brought General Motors into FANUC, kind of showed them what we were doing, and built up a lot of excitement within GM, and it resulted in us doing this proof of concept testing. So what we did here is took all of the hardware, the electrostatic changes, the process methods that we had developed, and then basically wanted to transition it from flat panel to a body panel type test. I'm sure most people are familiar with the in-plant test where you spray a car body, you have to weigh it. Makes it a little bit difficult in the lab. So with some of the recommendations from GM, well, I'll show you some video and how we did that testing. But at the end of the day, the main piece is we need to be able to hit the film builds, the color, the appearance. We still have to get those end results for the customer and for the end purchaser of the vehicle. And that is, you know, a driver in this high TE. In our testing, we've done prime, base coat, and clear coat layers, and to my knowledge, we're the only ones that have a metallic application in production running and painting to color and to standard. So our proof of concept resulted, or basically came out of this hood and fender testing, And what you see in this application, and it'll transition between production spraying and high TE spraying. And the differences are this hood and fender are in the position that it is in production. So we kind of made up this little jig to hold these parts, and then did the application of how it's being done today in the plant relative to how we would want to do it in high TE mode. Here the application, well, to do the calculation of the transfer efficiency in this test is basically the same as what we did with flat panel. We have the panel, we weigh it, we do the application, we know how much paint has been dispensed, bake the parts, and then are able to calculate the TE, which results in what we would consider a system TE that now the end user or the customer, in this case GM, could use to be able to gauge what could be done within the paint shop. So the results. So working with BASF and with GM, sprayed multiple different materials that Marcel will cover in a bit. But here in our gray metallic application, you can see an R value of 9 on a vertical surface and anywhere from a 0.5 to a 1 point increase in appearance in this application. A little bit on color, but we were able to meet the gray metallic color results without striping modeling and some of the issues that you would typically see. Also looked at black and similar application here, very good appearance results, and we saw that across all the materials that we had sprayed. Good TE, or excellent TE, good appearance, and actually saw an appearance bump in this application. So kind of summarizing what we did on the application, and working with BASF and with GM, we did have to see a little bit of a formulation change when it came to the base coat. If you think of it with high TE, everything that's being atomized is being brought to the part. So we're applying it a little bit wetter, drives some potential changes to the booth, whether it's in the temperature or the humidity conditions, to help with that dehydration. Minor changes in the materials for color match, to take advantage of everything on the high TE side. And ultimately, in some of the trials we did, we exceeded over 95% in that hood and fender test. So very good results comparing from the flat panel to what we consider our system TE. And then lastly, as I summarize my section, we were able to meet the targets that GM wanted. We transitioned it into 2 sites that Marcel will discuss, and we've had this in production now for 2 years, I think. And then the key to this is we can only do so much in the lab. I don't have the different tote of paint every day. I'm not changing the viscosities as production requires. So this gives us the ability to confirm how high TE works in a production environment. And with that, I'll transition to Marcel to discuss how GM has implemented high transfer efficiency.
Thank you, Matt. It's been a pleasure working with FANUC to bring this new technology from concept to reality. And I'm excited to close out our presentation by sharing how we implemented high transfer efficiency paint application at GM. Our goal was to see how the new technology would perform under actual real-world manufacturing conditions. That meant taking what was proven in the lab and implementing it at 2 key pilot locations. These sites allowed us to assess performance, appearance, and operational impact on actual vehicle production lines. I'll share how we utilize these 2 sites to trial a full body high TE application, and I'll share what we did, what we learned, and why we're excited about where this technology is headed. So with all the benefits you get from high transfer efficiency, we wanted to move quick. So we identified 2 greenfield 2-tone lines as ideal first implementations of the high transfer efficiency application. These sites allowed us to validate multiple paint technologies and multiple conveyance systems. The first site was a solvent-borne base coat with a 1K clear coat on a moving line, and our second 2-tone greenfield line was a waterborne base coat with a 2K clear coat at a stop station. Now, with the reduced overspray, high transfer efficiency enabled the dry filter scrubber and reduced boot downdraft and layout flexibility at both of these sites. And the layout flexibility proved very important, as both of these sites were already far along in the engineering phase when we decided to transition to high TE. So let me touch a little bit deeper into the layout flexibility that you get with high transfer efficiency. With the reduced overspray, you require less downdraft to capture that overspray. And also you are allowed to eliminate the wet scrubber, which is typically needed for its capacity to capture a lot of overspray. Here are some booth cross sections. And on the far left is our traditional spray booth that requires 4 levels of booth-related equipment. And I'll just take a moment and step through each layer from the top down, which is the direction of our airflow, to show what happens at each layer. So up in our penthouse layer, we have our recirculation air supply house. It's really nothing but fans in a big metal box. Inside that metal box is some filter banks and a chilled water heat exchanger or a cooling coil, and then also a hot water heat exchanger or a hot water or reheat coil. That air that is tempered in an air supply house travels through ductwork down to the plenum level. In the plenum level, there's some dispersion media that just separates out that airflow to provide a nice downdraft in the spray booth, which is the next level. That's where the vehicle is and all of our paint automation. The downdraft captures the overspray in the spray booth, and then it goes under the grates, and that's where the wet scrubber begins. And you can just think of a wet scrubber as a water wash. We are just, washing the air with water, taking the paint-laden air and putting that paint in the water. Water goes to the sludge room to separate out that paint, and that air leaves the wet scrubber, goes back up to the spray booth. Now the middle cross section is our high transfer efficiency spray booth, where we were able to delete the wet scrubber. That freed up the 0 foot level, and it's an ideal place to tuck in other equipment or even a conveyor, freeing up floor space and reducing the overall building size. The far right cross section is another site. It's also a high transfer efficiency spray booth. And at this site, we were able to remove the penthouse level by tucking the air supply house underneath the booth. So not only does high transfer efficiency provide layout flexibility, that equates to a 40% capital cost reduction, a 40% capital cost reduction for fabrication and install. So it removes the booth complexity. This isn't just layout theory. High transfer efficiency removes monuments and eliminates structural constraints that delay construction. So on top of all those capital cost savings, you couple in a lot of operational cost savings. So for paint savings alone, you'll get a 20% cost per unit savings, and that's in our two-tone line. When you read this across to a full body line doing a full surface area, it's a much bigger amount in actual real dollars. There's a reduction in Scope 3 emissions from less paint deliveries to the paint shop. And when you look at some of the comparisons in energy from the wet scrubber to the dry filter, well, one, you eliminate all the sludge water chemical treatment, and you'll see an 86% reduction in water usage. You get rid of all the blowdown of water and the water evaporation you get in a sludge tank because you don't even have a sludge tank, or the associated pumps that circulate that sludge water all year long. And another thing to think about is if you think about the utility load on the paint shop's chiller system and hot water generator system that you have with the wet scrubber versus dry filter, the air leaving the wet scrubber is close to 99% relative humidity. You've just washed that air with water. All that moisture is brought up to the booth recirculation air supply house, to the cooling coil, where all that moisture has to be condensed out of the airstream. Only to a few feet later, downstream, it hits the reheat coil to bring that air back up into the booth temperature and humidity set point. It's extremely inefficient. So on top of the improvement to the utilities, with the reduced downdraft, you can reduce the horsepower motors of your fans in your air supply house. When you add it all up, you'll see a 58% reduction in your booth energy usage. And you couple the paint savings, the water savings, and energy savings with some savings in booth management. You'll reduce your cleaning frequency, which will increase your uptime and increase your throughput. You'll also save some money on robot covers and improve your first-time quality. So after we've launched our two-tone chops, we began asking the big question, what would full-body high TE look like, and how can we get a sneak peek? So here you go. This is the same plant, two different lines, spraying the same body style. Both of these are clear coat zones. The video on your left is traditionally spraying. It's our main line. The video on your right is our two-tone line, high transfer efficiency booth, but we have reprogrammed these robots to do full body. So it's not exactly an apples to apples comparison, as there is throughput differences between these two lines, but it shows scalability, and high TE isn't just limited to niche two-tone lines. So I actually have to give a big shout out to FANUC, BASF, and Gallagher Kaiser for helping me with this trial, because we actually pulled paint out of the two-tone systems and loaded up a primer and a metallic, and we trialed interior spraying as well. So it was very stressful to get that two-tone shop back into its normal condition for Monday production. But yeah, this video speaks for itself. Tremendous amount of difference in overspray when you look at the two processes. So with the two-tone shops launched, we're back in the lab working on optimization. We're running DOE on our full color palette. And part of that was doing the speed trials that Matt alluded to earlier. Here's a side-by-side comparison of traditionally spraying clear coat compared to high transfer efficiency at an increased tip speed is up to 650. So you're not seeing the high 90% TE with the faster tip speed, but still a tremendous amount in paint savings. And it actually worked out to be pretty linear. As you increase the robot's tip speed, you increase the flow rates, and you lower the transfer efficiency. And there's a small drop in appearance as you go faster. You don't get that full 1-point improvement in R value. So while this video is playing, I'll take the opportunity to share another lesson learned that we discovered in the lab. If you think about the droplet leaving the bell cup, moving through its fan pattern to the vehicle, it's surrounded by dry shaping air for that 10-inch target distance. Well, with high transfer efficiency, we drop that target distance to 6 inches, and the result is we end up spraying a lot wetter. And as we try to increase our preset range, some of those variables can drive you into a pinholing or a popping defect because we're spraying so much wetter. You can tell just by looking at it, but we've also proved that with dehydration foil solids testing that we are spraying wetter. And one of the last things you want to do on an energy savings project is ask for a longer heated flash time. So one of the variables that we get to utilize that we typically don't utilize is the booth relative humidity set point. If you think about a wet scrubber, if we were to ask for a lower humidity set point, we would have to upsize our cooling coils, the piping systems and pumps, maybe even a chiller or add a second chiller, because that's more moisture you have to condense out of the air. But with a dry filter scrubber, you won't pay that penalty, that capital penalty or operational penalty from changing your booth humidity set point. We haven't reran the DOE through the color palette with the lower humidity, but it's a variable that we can keep in our back pocket if we need to. So this is just a general paint shop layout, and I'm only using this as an example to show the impacts of high transfer efficiency throughout the whole paint shop. It's not just the applicator at the end of the robot. You have an opportunity to reduce your booth abatement, reduce or eliminate your high pressure pumps that you use for cleaning grates and skids. You completely delete the sludge room, and you also eliminate the wet scrubber from underneath the prime and the top coat boots. Not shown here in this layout is the free space you get in the penthouse from the reduce downdraft in the smaller air supply houses, fans, and motors. So this isn't just an application change. This is a system-wide shift in how we design and operate our paint shops. So with all the benefits you get with high TE, we're saving water, we're saving energy, measurable improvements with paint savings and paint quality and paint appearance. These aren't just incremental gains, they're transformative, and they lead to a more sustainable and cost-effective future for our paint shops. Thank you. All right.
Okay, we have some time for Q&A. I'll start off with some that were submitted on the app. Does the reduction in booth downdraft impact paint appearance? And if so, did the material need to be modified to accommodate the change?
So the initial sites, we actually stuck with we didn't make any material changes, but I mean, going forward in our next full body shop, they'll probably adjust the solvent package, or I'm not a chemist, I'm more of an equipment person, so I don't know everything that BASF did for us, but in terms of the downdraft, our appearance is up one point in R value. So the downdraft, we've dropped it in half. Basically, we're just have the downdraft setting to make sure we capture dirt. But I mean, we're doing such a good job at putting the paint on the part that additional downdraft isn't needed to capture the overspray.
And I think you see that in the videos too, of some of the overspray that's cascading down the side of the car. You know, when you don't have that, you know, I think that's part of the appearance improvement. So whether it's 30 or 60 or 40, whatever the downdraft becomes, just having less paint being atomized better does help with that appearance.
For the two-tone, that was the example you were using. Were you able to, or are you considering changes to the masking as a result of getting this improved transfer efficiency, or is that not part of it?
Oh, that's a good question. We would love to be able to reduce masking. I mean, we're still atomizing paint in a paint booth, so our customer's never going to want an off-color paint on the primary color of the car. But yeah, there's definitely opportunity to not use as much of the plastic and tape.
Is the transfer efficiency impacted whether you're using it on a moving line or stop station? Looks like you had both examples in the green field there.
No impact versus the conveyance system.
What changed with the equipment hardware to improve the transfer efficiency, or was it just optimization through changing the parameters?
We made a lot of modifications to the applicator, to the electrostatic system, and then some process features that we kind of learned during the testing. So it's kind of a combination of all the atomization aspects of it, you know, starting with the smaller cup to get a smaller pattern, changes to the E-stat system to allow us to process at a closer distance. So a lot of little changes to be able to try to optimize this process to allow us to be able to do basically all the layers of the paint stack in production. So.
Okay. Were there any other changes necessary from other layers, sealers and E-coat or anything else?
No. Nope.
Labor savings from booth cleanings?
Yes. Yep. Reduced robot covers changes, reduced cleaning.
Yeah, and even during some of the initial lab trials we did, the way the panels were set up, it was amazing how both ends of the panel, you could basically walk up, pick up stuff, not have, you know, pretty much every piece of clothing I've ever owned in my life has some layer of paint somewhere, and this was the first time where, you know, you could bump into the table and not end up with a line across your pants or your shirt.
The filter change is a manual process. In the two-tone, I mean, we're way up in the upper 90% transfer efficiency because we're not spraying that full body. There is going to be some manual labor involved for changing filters when we transition to the full layering system on a full body.
Okay. Would probably be better if someone from BASF was up there with you, but were there any use of rheology modifiers, or was that a part of the project?
There is BAS people in the crowd, maybe they can. I can't answer that.
Yeah.
Any learnings when you went from the lab into production? Was there any fundamental change in how you had to approach it? Or, you know, what were the learnings going from lab to lab?
No, I mentioned a little bit in the lab we did see a popping or a pinholing defect, but you can see that spring traditionally as well. We were looking at model closely on our metallics, so there's some lessons learned there as well.
Any other questions? Going once, going twice.
It is
Okay.
almost lunchtime.
It's almost lunchtime. So, all right. Thank you to Matt and Marcel.
Thank you.